Hello everyone, my name is Riley Campbell, and for this final term presentation we'll be taking a deeper dive into the metal titanium as well as titanium dioxide. For this presentation I'm going to focus on a few key objectives, those being what exactly titanium is, then I'll talk about where it actually comes from, what is required to put it together as a whole for it to be titanium. Then we can talk about some products that are produced using titanium as well as products produced using titanium dioxide. Then we'll look into the physical and chemical properties. I'll also touch on the history of titanium as far as how it was first named, who it came from, what year exactly it was that titanium was named, which was different than when it was actually found. We'll touch on that a little bit later on. And finally, I'll talk about how the quality of titanium is tested. To begin this presentation, we need to understand what exactly titanium is. And titanium is a lightweight and strong metal that actually has its own symbol on the periodic table. It resides in group 4, and it has a silvery gray physical appearance to it. It looks like any other regular metal or steel. It's naturally found on Earth and it is known as the 9th most abundant element found and the 4th most abundant metal found on Earth, which is pretty interesting. Some of the key features of titanium that allows it to be more effectively used rather than any other metal is how lightweight but strong it is at the same time. It's completely corrosion resistant and it has a very low density. Before you can begin the manufacturing process to obtain titanium in its purest form, you have to obtain 3 primary ores that naturally occur on Earth. These ores are ilmenite, leucoxene, and rutile. While researching the How Products Are Made article, they give us a deeper background on why these 3 primary ores are necessary in creating titanium. That's mainly because ilmenite and leucoxene are known as titan-ferrous ores, which means that ilmenite carries around 53% titanium dioxide and leucoxene carries around 90% titanium dioxide. And rutile is relatively pure titanium dioxide, being roughly like 99.8%. And these ores are primarily found on beaches and in sand deposits. The How Products Are Made article also gave us a really good background in titanium dioxide and what's different than it rather than titanium in its pure metal form. And titanium dioxide can also be referred to as titanium oxide. Its form normally comes in a fine white titanium powder and is created naturally when titanium interacts with oxygen. It is extremely popular in everyday use, and you'll find titanium dioxide being used in a lot of products such like paper, plastics, toothpaste, sunscreen, and a lot of like wall paints and indoor paints. Now that we understand the materials that is required to manufacture titanium, we can look into the process that is actually required to complete this. And the most common process to produce titanium is the Kroll's process, which is named after William Kroll. We'll get into the history of titanium here in a few more slides. This process can be very lengthy and can actually take several days from start to finish. The only concerns with this process is that it can be cost efficient due to how long it actually has to perform. It's highly reactive and has to be closely monitored at all times, which is why it's also difficult. There's really no steps throughout this entire process that can go without being monitored by a human, not just a computer. And on the next slide, we'll look into how this process actually performs. Once you have acquired all of the required materials, you can begin the Kroll's process, which starts with the extrusion, which is the abundance of gathering up your ilmenite, your leucoxene, and rutile, and a few other materials. Then you begin in a large tank that has titanium dioxide reacting with a chlorine, which forms a substance known as titanium tetrachloride. This tetrachloride then reacts with magnesium that deteriorates the chlorine and leaves pure titanium as a result. And all of the magnesium chloride is actually, there's a ton produced during this process, and it's all recycled so that none goes to waste. Once all of this is recycled, you move on to the final step where you have your titanium, but it comes out in like a sponge form. So we call the product of Kroll's process a titanium sponge, but it is titanium in its pure metal form. On the ISQ directory about titanium, I found a lot of useful information that concerns the physical and chemical properties of titanium, but we'll start by looking at the physical properties. As mentioned before, titanium has a very, very high strength to weight ratio, which allows for it to be a replacement for a lot of steels when you require high reliability and strength but need it to be lightweight. Titanium also has a low density, which is around 4.5 grams over centimeters cubed. It has a extremely high melting and boiling point. For the melting point, it is 3,000 degrees Fahrenheit or around 1,650 degrees Celsius. Your boiling point, you're looking at 6,846 degrees Fahrenheit, which is extremely hot. Titanium also has a very low thermal and electrical conductivity. Continuing on with some more physical properties, once you are at 99.2% pure, you're now at your pure titanium form. Pure titanium is completely resistant to all sulfuric acids, chloride solutions, and organic acids, as well as your hydrochloric acids. Basically anything that can deteriorate any metals, titanium is completely corrosion resistant to, which makes it extremely beneficial. When it comes to the ultimate tensile test strength, we have 434 megapascals, which is a very, very strong metal. It happens to be around the equal strength of steel, but is also 45% lighter, as mentioned before, which makes it a very great replacement when you're needing a lightweight but very, very reliable and strong material. It has a Brinell hardness test of 70, and you only have around 54% elongation of where titanium hits its breaking point. Now that we've taken a look at the physical properties of titanium, we can look deeper into the chemical properties. And titanium acts as an inert element while oxygen and water is present. Titanium can only be melted when it's in a chemically inert environment, such as like a vacuum suction. It is typically very unreactive unless it is at a very high temperature. Taking a look at where titanium falls on the periodic table, it resides in period 4, group 4, which is nearly in the dead center. It has a periodic symbol of Ti. It consists of 22 protons and 26 neutrons. And since it has 22 protons, its atomic number is 22. And it also contains an atomic mass of 47.88. As I mentioned towards the beginning of this presentation, the history of titanium is actually quite interesting. And I found a lot of this information from the Ulbrich Metals article, which they're a company that produces titanium. And they stated that titanium was discovered by a couple of people rather than just one. It was first discovered in 1791 by an English geologist, William Gregor. Well, Gregor found this substance near a creek bed that appeared to contain a combination of a few materials. It was magnetite, iron oxide, and a new metal that he couldn't quite understand what it was yet. But 4 years later, after Gregor's discovery, a German scientist, Martin Klaproth, studied that a new material that he found that also contained a new metal that was similar to the one that Gregor had discovered. Klaproth was actually the one that named this metal titanium rather than Gregor. Gregor was the one that just found the material first but could not quite understand what it was. Once Klaproth named it titanium, he made the connection that this was also the same metal that William Gregor discovered 4 years prior. To continue on with the history of titanium, Titanium did not reach its purest form until 1910, which was produced by an American metallurgist known as Matthew Hunter. And the first use of titanium that was outside of a lab environment was in 1932 when William Kroll, who is the same person that the Kroll process is now named after, proved that titanium could be produced when reducing titanium tetrachloride with calcium. And this process took Kroll around 8 years to refine, using the experimentation of combining magnesium and sodium with his titanium tetrachloride. Now that we understand how titanium is produced, we can look into how it is applied to the real world. I found a lot of this information on the ISQ directory of titanium. And titanium is most commonly used in the aviation and aerospace industries due to its strength-to-weight ratio and it being completely corrosion resistant, which is extremely beneficial when traveling to space and anywhere at a high rate of speed. Also, it can be commonly found in the medical industry because of its biocompatibility, which allows the proper binding with human tissue with no infections or side effects. Titanium is also used for a variety of medical tools as well as implants, as I was just talking about. When used as a socket or bone implant or dental replacement, these implants can stay in the same place for 20 to 30 years due to its very low modulus of elasticity. Some more physical products that are produced by titanium are missiles and rockets, mostly airplanes also, they're around 50% titanium. Golf clubs, a lot of titanium golf clubs nowadays. Jewelry, although it's not as popular, there is titanium jewelry. Tools, knives, and swords, cell phone components, and automotive parts. While titanium is very useful in its pure metal form, it also has a lot of uses when it's in its titanium dioxide form. When it's in this dioxide state, it's more of a white permanent pigment rather than its metal form. It has a lot of different uses that are most commonly found in like papers, paint, plastics, toothpaste, a lot of home items. Titanium dioxide is also very important when you're producing cement and gemstones. When it comes to measuring the quality of titanium, the most two common ways are taking its tensile test strength and figuring out how pure titanium actually is. And the tensile strength of titanium is 434 megapascals. And titanium is considered to be at its purest form when it is 99.6% titanium. Now that we looked at how pure titanium in its metal form its quality is tested, we can take a look at the titanium dioxide quality test, which is used with two tools, which is the whiteness meter and the spectrophotometers. These two devices measure the quality of this titanium dioxide by examining the contrast of color, how weather resistant the dioxide is, how white the color comes off, and the overall color expression once mixed in with any other additives. Here I provided a few interesting facts that I came across when researching titanium. One was that titanium accounts for around 50% of materials that are used in any modern aircraft today, which I thought was kind of crazy to think about. Earth's crust is around 0.63% titanium, which seems like a low number, but once you factor in all the amount of materials and things that Earth's crust is made up of, it's actually a pretty high percentage. Like I said, it's the 9th most abundant element on Earth and the 4th most abundant metal, which is pretty cool. It's twice as strong as aluminum, and nearly 95% of titanium is used in its dioxide state, as I was just talking about on the previous slides, that the titanium dioxide is actually where you'll see titanium being used the most, as it has its most uses, rather than just it in its pure form. Also, since the pure form is really hard and cost effective to produce, the dioxide state is a much more useful route when using titanium products. And the original name for titanium was manganese. I hope you all enjoyed this presentation on titanium. These are the references that I used if you would like to check out any of the links and find any more information on titanium. I found all of these articles to be extremely useful and packed with information.